Okay, Assalamualaikum and good morning. Alright, so today I'm going to teach you on chapter 7, which is on LTI discrete time system in the transform domain form. Okay, so if you look at the title itself, okay, we have two keywords. One is linear time invariant discrete time system. Another one is transform domain. Okay, so basically when you see the keywords transform domain, definitely you know that it is must be in his Z form. Okay, so basically the equation is coming from his Z domain. Alright, so when we talk about his Z, so maybe some of you may wonder why we have chapter 6 and why we have chapter 7. Okay, so basically chapter 6 is basically on for us to determine the ROC. Okay, so for you to determine the ROC, you need to have the post value. So where to get the post value? You get from the denominator part. But in chapter 7, we are going to look at the zeros value. So where to get the zeros value? It is coming from the numerator part. Okay, so that is the difference between chapter 6 and 7. Okay, so I'm going to repeat again. Chapter 6, you need to determine the post value. So based on the post value, you can determine the ROC of the system, the region of convergence of the system. And in chapter 7, you have to determine the zeros value. So from the zeros value, we can determine the condition of the system, either it is maximum phase, minimum phase, or mid phase. Okay, all right, so okay, we start with the introduction of the chapter. Okay, so first, time domain classification based on length of impulse response system Hn. So basically we have Hn. Hn is in time domain form. Okay, so Hn can be finite FIR or infinite IIR. So it can be both. It can be finite or infinite. Alright, transform domain classification is based on magnitude of phase characteristic of transfer function of system Hz or H exponent j omega. Okay, why we still have H exponent j omega? Okay, so basically if you still remember Hz Z transform is determined is actually the transformation from time domain to frequency domain. So basically, the time domain form must be in discrete time signal, which is Hn. So that is why instead of we use Hz, okay, in some literature we can see instead of they use Hz, they still use H exponent j omega, just to indicate that the signal is discrete time signal. Okay, alright, so basically in this chapter you will learn on the phase. Okay, so basically you will see linear phase, maximum or maximum phase or zero phase. First, we start with all pass transfer function. So what is all pass transfer function? So NIIR transfer function Hz with unity magnitude response for all frequency, that is modulus H exponent j omega squared equal to 1 for all omega. So basically if you look at here, this is actually the magnitude of the signal. So magnitude of the signal must always equal to 1 for all omega, for all frequency. Alright, so we have the example, an m order causal real coefficient of pass function is of the form. Okay, so here we have hmz equal to dm plus dm minus 1 z minus 1 over 1 plus d1 z minus 1 plus blah blah blah. Okay, so if you look at this transfer function, this transfer function is actually similar to chapter 6. Okay, so basically for you, for chapter 6 and 7, the transfer function must start, for denominator part, it must start with constant 1. So what happens if this constant 1 is not equal to 1? So let's say, for example, we have 3. So what you have to do is you need to do factorization so that we can kill off that 3. Okay? Alright, so next, letting the denominator polynomial to be dmz. So we have our denominator part. Okay? So then it follows that HMZ can be written as, so basically if you look at this equation, it is already factorized. So basically the equation must be in factorized form. Okay, note if z equal to r exponent j theta is a pole of HMZ, then it has a 0 at z equal to 1 over r exponent j theta. Okay, so basically if you look here, it did mention that, okay, because of this condition, okay, it shows that the poles and zeros value are actually the mirror image of each other. Okay, so if we put it in illustration form, the X represent poles placement. Zero represent the zeros placement. Okay, so if you are asked to place the zeros and poles value in what to say, in magnitude phase spectrum, so basically you have to sketch this one. Alright, so if you look here, we have the poles inside the unit circles, and then we have the mirror of the poles, which is zeros, okay, which is outside of unit circle, and then instead of it is at the positive side, okay, so instead of we have the, okay, the zeros value is in unit circle, and then it is at the positive quadrant. If you look here, when we want to place our poles value, it is actually outside unit circle, and also it is at the negative quadrant. So how I know it is positive or negative quadrant? Okay, I hope you still remember your maths. Okay, so if you look at this graph, we actually have 4 quadrants. Okay, we have positive quadrant. Okay, here is negative quadrant, here is negative quadrant, and here is actually negative quadrant. Okay, so this one is coming from your maths. Okay, next we move to property of all pass function. Okay, we have 3 important property of all pass function. Okay, so basically important property of a causal stable all pass function. Okay, in chapter 7, we must make sure our transfer function is causal function, and also at the same time the function must be a stable function. Okay, so if you still remember, causal means the signal is at the right-sided sequence, or in other words, it is at the right-sided region. When it comes to stable, stable means the transfer function must include unit circle. So stable include unit circle. So basically, your transfer function must be in the right-sided sequence, and also that sequence must include unit circle. Okay, so a causal stable real coefficient all-pass transfer function is a lossless bounded real transfer function, or equivalently, a causal stable all-pass function filter is a lossless structure. If you look here, okay, the magnitude all-pass transfer function, okay, as you can see here, we have, okay, for modulus z greater than 1, all the values is less than 1. But if modulus z equal to 1, the value is 1. And if modulus z is less than 1, the value is greater than 1. So if you put it in a graph, you can see, okay, when modulus z equal to 1, so it is, the value is 1. Okay, so when modulus z is less than 1 means 0, minus 1, minus 2, the value is greater than 1, so more than 1. But if modulus z is greater than 1 means 2, 3, 4, the magnitude value is less than 1. So basically, if you can see here, this is the magnitude of stable all-pass function. Okay. Alright, so next, the properties of all-pass function. Okay, based on the all-pass transfer function, you can determine the group delay and phase response. So one of the example of all-pass filter is the application of delayed equalizer. Alright, so next we move to application of all-pass function. Okay, we have digital, we have input, XZ, and then we have output. So this YZ is your output, XZ is your input. Okay, and that our input will go to digital filter with prescribed magnitude response GZ, and then the GZ will go to digital equalizer, which indicate by HZ. So okay, instead of we use GZ, okay, this one the same thing, still we have the digital time signal. Okay, see, so we have G exponent J omega equal to modulus. Why modulus? Because we just want to have the causal system. Okay, means all the values must be at the positive side. Okay, that's why we have modulus. Then we have G exponent J omega times H exponent J omega. But since modulus H exponent J omega is always equal to 1, then your G exponent J omega is always equal to modulus G exponent J omega. Okay, next we look for zero phase transfer function. Let Hz be a real coefficient rational Z transform with no poles on the unit circle. Then Fz equal to Hz times H inverse Z has no zero phase on the unit circle. So basically, if we have no poles value on the unit circle, then we also have no zero phase value on the unit circle. Okay, if you still remember the illustration just now, poles and zero are mirror image to each other. Okay, so basically if we don't have poles value, then of course we don't have the zeros value. Okay, resulting in poles for Fz located as mirror image symmetry of each other, so too the zeros are also mirror image symmetry of each other. Okay, let's say if Z equal to V is a poles, then as is Z equal to 1 over V as another poles for Fz in Z plane. That means it is impossible to implement a causal digital filter with zero phase. So if Hz is causal, then Hz inverse will be anti-causal or vice versa. Okay. So next we move to linear phase transfer function. Okay, so if you still remember, when we have linear phase, okay, so for example, yn equal to Sn minus t. So by taking off DTFT of Yn, then we have the time, and we apply the time shifting property. So we have y exponent j omega is coming from DTFT of Yn, and then we have delay. So basically DTFT of delay, we have exponent minus j omega d, and then we have xn. So xn, the DTFT of xn is x exponent j omega. So by seeing this, we can actually determine our h. So h exponent j omega is equal to y over x. So basically, after we bring down your x, then you just have exponent minus j omega d. Okay, above frequency response has a unity magnitude response and linear phase with a group delay of d samples at all frequencies. That is, we have modulus h exponent j omega equal to 1, and then theta omega equal to minus omega d. So tau omega equal to minus d theta omega over d omega equal to delay. Alright, so when we see the linear phase, of course it is interrelated. It is related with the symmetrical condition. Alright, so basically for a finite sequence, we have two types of sequence. We have symmetrical sequence, we have antisymmetric sequence. So basically, when you see term symmetric, of course you know that xn equal to xn minus 1 minus n. So basically, capital N is coming from length n. Alright, so when we have antisymmetric, definitely anti, so we have minus. Okay, symmetric just now, it is just positive, no negative. When it is anti means we don't like, we dislike, then we have to put minus. Okay, so now we move to linear phase. So basically, linear phase, this is the equation. So you can see the illustration of linear phase. Alright, so under linear phase, we have two types of length. Okay, one is odd length, another one is even length. Okay, so if you look at even and odd, alright, so for odd length, okay, we have n equal to 7. Okay, and then we have n equal to 6 for even length. Alright, so under odd and even, we have type 1, type 2, type 3, and type 4. Okay, so basically, if you look here, what is the difference between them? Alright, so for you to know either the system is linear phase or not, you have to look at the value. So if you look at this value, okay, so for type 1, for example, we look at type 1 n equal to 7. So n equal to 7 is odd length. Okay, why we have 7? Okay, so if you look at the graph, we have n from 0 to 6. Okay, so if you sum all together, it is actually equal to 7. Okay, so if you look here, okay, the values, okay, for you to know the symmetrical thingy, okay, you have to imagine you have a cloth, then you need to fold your cloth. Okay, so what happens when you fold your cloth and then you operate again, you can see a line, a center line. Okay, so basically the center line is your symmetrical line. Okay, so if you look here, you have a sequence. So what you have to do is, the sequence is from length 0 to 6. So what you have to do first, you imagine you fold the sequence. You fold the sequence and then you operate again. Okay, you can see the symmetrical line, and that symmetrical line is actually for, okay, the symmetrical line is actually for the symmetrical line. Okay, so basically the symmetrical line is actually for the symmetrical line. Okay, you can see the symmetrical line, and that symmetrical line is actually for the symmetrical line. Okay, so basically the symmetrical line is actually for at n equal to 3. So basically at n equal to 3 is your center of symmetry. Same goes to type 3. Type 3, okay, we want to know it is linear freeze or not. Okay, so basically we have to fold the sequence and then we open it again, and we know that the center of symmetry is at n equal to 3. Okay, for even length, for example n equal to 6. Alright, so what happened? The sequence length is from 0 to 5. So you imagine you fold the sequence and then you can see the symmetrical line. So if you look here, the symmetrical line value is at n equal to 2.5. Okay, same goes to type 4. Okay, it is in between 2 and 3, so the value is at n equal to 2.5. Alright, okay, so basically for you to know, you have to actually sketch the graph. Okay, I mean sketch the values lah on the graph. Okay, so next, okay, we want to look at either it is symmetric or antisymmetric. Okay, so if you look at, okay, if you look at this equation, xn symmetric is xn minus 1 minus n. So for antisymmetric, it is xn minus xn minus 1 minus n. So if you compare here, okay, type 1 and type 2 is symmetric sequence. Why symmetric? Because of, if you flip the value, you can still get the same value, right? Okay, if you look at 2 equal to 3, n equal to 2 and n equal to 4, you still have the same magnitude, right? You have the same magnitude, 4, 2 and 4. Okay, same goes to others, you have the same magnitude. When you look at n even for type 2, still you have the same magnitude at the positive side and also at negative side. But for type 3 and type 4, type 3 and type 4 is actually antisymmetric. Why antisymmetric? Okay, if you look here, the positive part is actually the reverse part of the negative part. Okay, the value of negative part at type 4 is also the reverse magnitude of the positive side of type 4. Okay, so basically symmetric means if you fold and then you found that your positive and negative side, you have the same value for positive and negative side, so it considered as symmetric. Okay, you can see in type 1 and type 2. But when we talk about type 3 and type 4, it is antisymmetric sequence. Why? Because of we have the reverse values for positive side and negative side. Alright, so basically this is the basic. Okay, so I hope you understand this one. Okay, so in this note, okay, I have the dotted line, red dotted line. So the red dotted line is actually the center of symmetry. Okay, so next, okay, how about the group delay? Okay, group delay is the values about symmetrical point. Okay, so basically if you look at this example, type 1, type 2, type 3 and the type 4. So basically you need to determine the center of symmetry, right? So basically the values of the center of symmetry will be the group delay value. Okay, so next I give you one example. You need to determine what is the group delay values of type 1 n equal to 7, type 2 n equal to 6, type 3 n equal to 7, and type 4 n equal to 6. Okay, so basically I know you can answer this one. Type 1 n equal to 7. Okay, so you look at this one, type 1 n equal to 7. So center of symmetry is at n equal to 3. So basically for type 1 n equal to 7, the group delay is at n equal to 3. Okay, for type 2 n equal to 6. So you refer to this graph. Okay, so you look at this, your center of symmetry is at n equal to 2.5. So definitely you know that the group delay for this one is at n equal to 2.5. Same goes to type 3 and type 4. Type 3, done. So very easy, right, for you to determine the group delay. So basically group delay is depend on the center of symmetric value. So how to get the center of symmetric value? You have to imagine you fold the sequence. You fold the sequence. If the value at the positive side is same with the negative side, then it is symmetric sequence. But if the value at the positive side is the reverse value of the negative side, then it is considered as antisymmetric sequence. Alright, so basically under this subtopic, okay, you will have the impulse response Hn. Okay, and the impulse response sequence is given in time domain sequence. And then under this subtopic, you must make sure you know you can determine what is linear phase. Okay, so go back to definition. Linear phase is symmetric about center of symmetric. Okay, when we talk about causal, if Hn equal to 0 when n less than 0 means the system, the phase is causal phase if it is right-sided sequence. And basically from this subtopic also, you must be able to determine the group delay value. So basically where to get the group delay value? From the center of symmetry. Next, in this chapter, you must able to understand what is minimum phase, what is maximum phase, and what is the mid phase. So if you look here, we still have causal and stable transfer function. Okay, so how to make the system causal and how to make the system consist of causal and stable transfer function? Okay, first you must identify what is the condition. You must determine the phase of the system. Okay, so first, what you have to do first, you must remember the equation. I mean, not the equation, you must remember the definition. So, these three definitions you must remember. So basically, minimum phase definition, all zeros. Okay, this time around we use term zeros. You need to determine the zeros value. So basically, from the zeros value, you can determine the condition of the phase. So for minimum phase, all zeros are inside unit circle. Means all zeros value must be less than 1. Okay, when we talk about maximum phase means all zeros are outside unit circle. Means all zeros value is greater than 1, then it is maximum phase. But if the zeros value is inside and outside unit circle, for example, you have the zero value at 0.5 and another one at 2. So basically, it is considered as mid-phase system. Alright, so next, okay, if your system is minimum phase, then the system is causal and stable. You don't have to worry a lot. But if the system is minimum sorry if maximum if the system is maximum or mid-phase function, then you need to worry. Why? Because of you need to get the causal and stable phase, the causal and stable transfer function. So, how to create the causal and stable transfer function? Okay, based on maximum or mid phase function, you can determine minimum phase function and all pass function, or you can also determine the minimum phase function and linear function. Okay, so I'm going to show this one on in example later on. Alright, so basically that's all for chapter 7. Okay.